Okay, so this video is going to be on the fundamental theorem of algebra, which you have most definitely looked at before, but maybe didn't realize this is what it was called. And typically you learn it over several days, so this is going to be kind of a lot of notes. It'll be a long video. So the first bullet is, just in describing this, is the fundamental theorem of algebra says that a polynomial of degree n has n number of roots. So if you guys recall, the degree of a polynomial is the highest exponent that the polynomial has. So if it was like y equals 3x to the fourth plus 5x squared plus 2, then 4 would be the degree of the polynomial, and then you would know that it had 4 roots. Next, a polynomial can be written in terms of its linear factors. So in terms of its linear factors. So we might have like f of x equals a. The a represents like a stretch or a compression or whatever, some sort of coefficient. X minus r sub 1, this is the first root, the second root, and so on and so forth until whatever you get the degree to be. So these r values, they could be nice numbers like 5 whole numbers, or they could be radicals like the square root of 2, 1.41, or they could even be complex numbers where they have like a real component and an imaginary component, so there's like an I in there. So the r's, the r1, r2, rn, are real or complex roots. All right. Next, complex roots come in pairs. And this you might realize it makes sense, because if you think about what we know about complex roots, they come from the quadratic formula. That's how we solve for them. And with the quadratic formula, the part that becomes the imaginary number is because you have a square root underneath a negative, or a negative underneath a square root, excuse me. And square roots always have a plus minus in front. So that plus minus, you have two versions, the positive version of the square root that became imaginary and the negative version of the square root that became imaginary. So they always come in pairs, there's always two of them. The next bullet is a factor can appear more than once. And the number of times that it appears is called its multiplicity. Okay. So those are all the important parts of the fundamental theorem of algebra. So now what we're going to do is we're going to look at like the practical application of how we can use these to like sketch graphs or to take graphs and write equations. So first we're going to look at the degree of a polynomial, and that's going to help us determine the end behavior. So the degree of the polynomial determines end behavior. So hopefully you recognize this. You can draw a little sketch here. It doesn't have to be super accurate. If you had a parabola, parabolas are U-shaped like this. So that's x squared. If you were to graph something that had an x to the fourth, it would look generally U-shaped. It's possible that somewhere in the middle of the U would get kind of squiggly in the middle, but overall it would be U-shaped to just be a little bit more narrow than an x to the second. And then an x to the sixth would be the same thing, but it would be even more narrow. Right there. So this would be like an x to the second, x to the fourth, x to the sixth, etc. Right? So here, if we look at this graph, the end behavior of this graph is going to be arrows going up if it's a positive coefficient. So if this graph was positive. If it had a negative coefficient in the front, it would flip those upside down, so you'd have two arrows going down. So that'd be a negative coefficient. So this is the like informal notation for that. So now that we're in pre-calc, we're going to do something a little bit more formal. So for the positive coefficient, I'm only going to write it one way, and then I'll let you guys figure out how the other way works. So if you, for the positive coefficient version where you have the arrows all going up, we would say as x goes towards negative infinity, so that means as x is going left forever, those y values are going up. So we would say as x goes to negative infinity, f of x, the function, or the y values, go to positive infinity. And then we would say as x goes to positive infinity, or as it goes to the right, the function still goes up. So the function also goes to infinity. Okay, and then we also have the other versions. So this took care of our even exponents. If we have a graph with an x to the 1, that's a linear, so that's a straight line. A cubic function goes up like this. It's like half a parabola going up and half a parabola going down, so that's an x to the third. An x to the fifth graph would go up. It would just be more narrow and go down like this. And again, if we had like x to the fifth minus 3x squared plus 7, it'd be kind of squiggly in the middle, but overall it would have this general shape. So this is like x to the 1, x to the 3, x to the 5, x to the 7, etc. So with these, what we'll notice is that first it goes down and then it goes up for the end behavior if it has a positive coefficient. And if it had a negative coefficient, then it would start up and go down. So it would be like a downward slant. It'd go this way. And that's if it had a negative coefficient. Okay, so formal notation for the positive coefficient, we would say as x goes left, as x goes to negative infinity, f of x goes to negative infinity because it goes down. And as x goes to the right, positive infinity, f of x goes up, which is also positive infinity. Okay, so next we're going to talk about the shape at each of the x-intercepts, or at each of the roots. So what you need to write here is that the multiplicity of the root determines its shape. So, for example, let's say here is our x-intercept right here. If our linear factorization was written like this and it had no exponent, which really means it has an exponent of 1, then that root is linear. So the line would go straight through that point. So we have two options. We can have the line going straight through slanting up, or it could go straight through slanting down. So here's our two options, straight through up or straight through down. Next, we could have a root that's written like this, and it could have a multiplicity of 2 or 4 or 6 or 8. And what that would mean is if this is the root right here, then you either have a mini parabola sitting above the root or a mini parabola coming up from underneath the root. So possibly like that. So this is what these would look like. And then these would have going straight through the root. Okay. And then our last scenario is if we had something like x minus r to like the third or the fifth or the seventh. And these are called S-curves. So they look like half a parabola going up and half a parabola going down. So either the S-curve looks like this, where this is the root, or the S-curve looks like this, and that's the root right there. Alright, so now we're going to use what we know to sketch graphs. So for this example, it's going to say sketch the graph of the polynomial. And we're going to have y equals negative x times x minus 5 times x plus 2 squared times x minus 3 to the third. And this is called this form would be called linear factorization form, so it's the linear factors. That's how it's written, as opposed to standard form, which would be like something x to the fifth, and then x to the fourth, and then x to the third, and x to the second with pluses in between all that, no parentheses. Okay, so what we're going to do here first is we're going to look for the overall degree. And the degree on this is kind of hidden since it's not multiplied out. So you just have to picture what would happen if you were to FOIL all of these things out. So if this one is an x to the 1 and this is an x to the 1, so if I multiplied those, I'd get an x squared. If I wrote down 2 of these, then I'd have an x squared there. I'd multiply that, get x to the 4th. So basically what you do when you're looking at the degree of these is you add all the exponents together. So I've got 1 and 1 and 2 and 3, means that overall if I multiplied that out, I'd have a degree of 7. So this is an odd graph, so the end behavior is going to be 1 up and 1 down. And since it has a negative coefficient, that means it goes up first and then it goes down. So next we want to look at the roots, and we've got 0 and 5 and negative 2 and 3. And each of these have different multiplicities. So 0 has a multiplicity of 1, 5 has a multiplicity of 1, negative 2 has a multiplicity of 2, and 3 has a multiplicity of 3. So for this one, it's either going to go straight up through the root or straight down, straight up or straight down. These ones are going to have many parabolas at the root, and then this is going to have an S shape at the root, or like a mini cubic. Okay, so we're going to sketch the graph, and when we draw these graphs, we only label the x intervals. We don't label the y, and that's because if we were to plug these y values in, they'd be huge. If you can imagine, even a small number raised to the first, then raised to the second, then raised to the third, and multiplied together would be very large. So we don't label the y-axis at all, but we label the x, and then I'll go ahead and put my roots in there. So I just put these 4 roots in there, and I know that this arrow is going to start up, and then over here it's going to end down. So I just put those because it kind of helps me guide where I should go. So first, through negative 2 is a multiplicity of 2, and now here's where we just use some common sense. So here I know I need to draw a parabola that's either underneath the graph or above the graph, and if this is where the arrow is coming from, then it must have been above the graph. So there's my little parabola shape. So starting the graph right there. Through 0, I have a multiplicity of 1, so I have to think, should I slant up through the point or down through the point? And slanting down through the point makes more sense. So we're going to slant down through the point. Here at 3, we have a multiplicity of 3, so I need to picture which one works. And this one makes more sense to have this part going down and then this part going up like that. So there's my cubic, the cubic shape. And then the 5 is a straight line, so I'll bring it up and then go straight down through 5 and end with my arrow going down. Also be careful to make sure that these are smooth curves. You should not have anything coming together looking like a V shape at all. Okay, next we're going to go ahead and take a graph and then write the equation from the graph. So the directions here are write the equation of the polynomial using its linear factorizations. Alright, so we're going to start at -4 like this. And we're going to start with an arrow down and go up like that. And then we're going to go through -1, like that. And then at 2, we're going to hit it like that. Okay, so the first part I want to look about this is the degree. And I can see from this that the degree must be even because both arrows go the same direction. So I know that I'm going to have an even exponent. And I know that because both of these arrows go down, it's going to have a negative coefficient. So that's good to note. And then what I want to look at is what all my roots are. So this root right here, 1, 2, 3, 4, it was -4. That means in the parentheses it would be x plus 4. That's what would have given us a root of -4. And this is a cubic right here, so it would be an exponent of 3. This part right here is a -1, so it would be x plus 1 in the parentheses, and it goes straight through that point, so this one would have an exponent of 1. Over here, this root was +2, so in the parentheses it would be x minus 2. And then because that's a mini parabola shape right there, it should be squared. All right? So if I add these up, 3 plus 1 plus 2 makes 6, which fits what I expected for the even degree. So now I know it's going to have a negative coefficient, so I'm going to put a negative in the front. There's not enough information for us to tell if there's a stretch here at all, and so we're going to not put an a for now. We're just going to ignore that part. And then in the front, I'm just going to put f of x equals, or you can put y equals, just to make sure it's written like a function.